Each year, thousands of tourists come to see the Grand Canyon of the Colorado River. Few other places on the earth reveal such a wide span of the Earth's history. The weathered and eroded remains of igneous and metamorphic rocks make up these layers of sedimentary rock. Geologists can read a story in these rocks because each layer is like a page in the Earth's history. So let's look at some sedimentary rocks and see if we can read their stories. All of the forces of weathering and erosion that work on the land have one central theme: the reduction of the land to sea level. Weathering breaks down the rock chemically and physically. Water, wind, ice, and gravity move the material downhill. The material eventually reaches a resting level. The level may be temporary, behind a waterfall or at the base of a steep slope like one of these. Or it may be permanent, as in the bottom of an ocean basin. In any event, the result is the same. The material is deposited. And the way it is deposited depends on the agent responsible for erosion and transportation. If the material is buried and cemented, it will form sedimentary rock. So by looking at the sediments being deposited today and comparing them to the sedimentary rock, we can learn something of its origin. One type of sedimentary rock forms from sediments in streams. Where fast-flowing streams flow out onto a valley and slow down, the heavier sediments of sand and gravel can no longer be supported in the water, so they sink to the bottom or pile up in bars along the stream channel. A mixture of sand and gravel has been cemented into this rock called a conglomerate. Conglomerates are often found at the base of a cliff or at the bottom of a steep slope. Geologists now know that conglomerates indicate that a fast-flowing stream slowed rapidly and deposited the material that later formed the rock. So we can use its presence on a flat surface to map the kind of terrain that existed there millions of years ago. When grains of sand are cemented together, the rock they form is called a sandstone. By studying the features preserved in the rock, geologists can tell whether the grains were deposited in the bed of a stream, in a beach, a river delta, or a sand dune. Geologists have observed that where water flows over a smooth sand surface, ripple marks are often developed in the sand. These are in a tidal pool. They closely resemble ripple marks that have been preserved in the sandstone of this Utah desert. So ripple marks are one clue geologists can use to determine how this type of deposit was formed. Water flowing normally in a stream bed will scour and fill the channel, laying down a series of beds in alternating directions. Geologists call this kind of deposit cross-bedding. When it is preserved in the rock, we can use it as evidence that flowing water formed these deposits. Along shorelines and in deserts, wind-blown sand forms large dunes. The constantly shifting wind forms large cross-bedded layers of sand. An alternating pattern of layers develops just as in the stream channel. They are strikingly similar to these in the sandstone cliffs of Zion National Park. But since such cross-bedded layers can be formed either by water in a stream or by wind in a dune. Geologists must look further to tell which process formed these layers. Under the microscope, a sample from the rock in the cliff shows grains smooth and rounded with a frosted surface. Wind is the only agent that produces such round, frosted grains, so the cross beds in this cliff wall must have been formed in a sand dune, not in a stream bottom. When a stream enters a larger body of water, the material it drops forms a delta. This sandbank shows a cross-section of deposits from a stream delta. The sloping beds were formed as water poured mud and sand down the sloping front edge of the growing delta. Thus they are named foreset beds. Eventually the slope lessened, and the beds on top, called topset beds, were laid down as a nearly horizontal layer over the foreset beds. So when top and foreset beds like these are preserved in rock, they indicate that the sediments were part of a stream delta. A meandering stream may change its channel several times in a century. Finer and finer sediment may be deposited in a process that is repeated with each change of the stream. A cross-section of the rock formed from such deposits shows a series of layers, with the large sands and gravels on the bottom. As we move upward, the sediments are graded into finer sands and finally into shales. Above the shale, another coarse layer repeats the cycle from coarse to fine material. An erosional surface on the top of the shale marks the return of the stream where the cycle started over once again. Such graded beds tell of a cycle of deposition by a stream, followed by erosion. Often, dozens of graded beds are piled one on top of another, indicating that the process was repeated many times over thousands of years. In swampy areas, water flows very slowly, and only the finest material can be carried and deposited. When such deposits are cemented to form rock, the result is shale. Layer after layer of shale has been built up in these formations in the Badlands. This shale and the many fossils it contains indicate millions of years of swampy conditions in this part of South Dakota. When the climate was dry, the swamp or mudflat dried out and cracked. Sometimes this too has been preserved in the rock. These rock faces in Virginia clearly show the original cracks in the mud. The once flat-lying beds were tilted during the formation of the Appalachian Mountains. Raindrops also dented the surface of the mudflat and have been preserved in the rock. If the plants in a swamp grow generation after generation, successive layers of partly decomposed material may accumulate and slowly be converted to peat and later to coal. Often, layers of shale interbedded with the coal contain the imprints of plants that grew in the ancient swamps. In the oceans, the process of living and dying also produces sedimentary rock. waves concentrate broken shell fragments and bury them under layers of sand. Groundwater may help cement them together to form a rock we call coquina. In warm, quiet water, small animals called corals build reefs of limestone on the ocean floor. The reefs are a refuge for many fish and marine organisms. In Texas, an ancient coral reef has been raised several thousand meters above the present sea level, but it was once at the bottom of a tropical lagoon. Where seas were landlocked and dried up, they formed great salt flats made of sediments called evaporites. Rock salt, anhydrite, and gypsum are typical examples of minerals that collect when the climate causes water to evaporate. When conditions are just right, great quantities of calcium or magnesium carbonate may be precipitated from the ocean waters in which they were dissolved. Such material often cements shells or coral fragments, forming limestone or dolomite. In the United States, great beds of limestone like these cover the states of Tennessee, Kentucky, West Virginia, and Virginia, telling of seas which vanished long ago. The plants and animals which lived in those seas left their marks as fossils. In this piece you can see the fossil remains of animals which lived on the sea floor long ago. Conglomerates, sandstones, ripple marks, the shape of sand grains, and fossils are just a few of the things geologists use to read the Earth's history from the rocks. If you look closely the next time you pick up a sedimentary rock, maybe you'll find it has a story to tell.